Today we're going to go over worksheet number 2, and we're going to get started on, I'll answer any questions you guys have about worksheet number 1. Whoa.
I was going to say the confusion for a second, but I have that statement, so we're okay. State of liquid averageness.
Plasma. It's like my husband has a dad joke that's like, I'm in shape. Round's a shape, right? He's not round. All right, guys. We are going to go over some of the parts of worksheet number 2 that we didn't cover before. So let's see. We've got, for problem number 4, the object moves in a positive direction at a steady speed for 10 seconds. So that tells us that our dots are all going to be equally spaced out. Let me fix my camera. I'm trying to do this so that with my videos, you can see what I'm writing. So we're going to have, for the first part, we're going to have equally spaced dots. Oops, dots. Then it reverses direction, so it goes in the negative direction and moves back toward the negative at the same speed. So the same equally spaced dots, but opposite direction. Opposite direction. All right. So let's see how you guys did on this. So I'm going to start here with time equals 0. It doesn't say where I started, so I can start anywhere I'd like. And then I'm going to draw 10 seconds worth of dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That should be 11 dots across there, right? Because I need 1 for 0 seconds. So here's where time equals 10 seconds. And then my object is going to go the other way. This is a little bit tricky because here I've got a dot that's at 10 seconds. But after this dot, I'm moving the other direction. So when I go to draw my arrows, I got 10 arrows going across here for my 10 seconds. Now my spacing could have been better. But after this point, I should be going the other way. So what I like to do is instead of drawing it there, I'll actually move this dot down here so that when my object changes direction, I can draw an arrow from it. So I need 10 seconds going the other direction at the same speed. So I'm going to have the same spacing. So I'm just going to kind of refer to my previous dots here. I'm just doing the best that I can. Just try to make it look like you tried. And then I have arrows pointing in the opposite direction, which is an indication that my object is moving the other way. How'd you guys do on that part? Pretty good? T equals 20 seconds. Now, when we're trying to draw our velocity versus time graph, remember in Unit 2, we have constant velocity. So what that means is that when we look at our velocity versus time graph, then we're always going to have a straight line. So that's why in our previous ones, we always had horizontal lines. Down here, we're going to also have horizontal lines. We know that these are going the same speed, but they are going opposite directions, which means the difference in our velocity isn't the magnitude, it's the sign that goes with it. In the first 10 seconds, we have a positive velocity. In the second 10, we have a negative velocity, but they have the same value. So when I look at my graph, there's a couple of things I'm going to know. I'm going to note that I have a positive velocity. I know that I have a negative velocity. And I know that something changes at 10 seconds. So the way that my graph is going to look is I'm going to have that constant positive velocity until 10 seconds. And then at 10 seconds, I switch to a negative velocity and continue. So there's a couple of things, a couple of places where students make mistakes. The mistake that I made earlier today is I accidentally drew like a position versus time graph. It happens. The other thing, you don't need to draw a vertical line here, because if you drew a vertical line, what you would be saying is that at that time, your object had all of the velocities between the positive velocity value and the negative velocity value. And that's just not how objects work on Earth, right? They just don't. They have one velocity. Okay. And it's also important to include that time thing here, because there are two different chunks of motion here. We've got the first chunk, we're going the positive direction, and the second one, we're going the negative. Do you guys have any questions about number 4? How'd you guys do? Okay? Yeah. Okay. All right, on the back side. So our first one, position versus time. Did I do these with you guys? Or was this from the other class? Okay. So we've got slope of position versus time is velocity. That's important to keep in mind. So if we have a graph that's position and time, that slope gives us velocity. Again, because our theme this unit is constant velocities, we're going to have straight lines on velocity versus time graphs. Same thing happens with problem number 6. We've got 2 different parts of our motion. The first part is 1 meter per second. The second part is minus 2 meters per second. So on our graph, we need to make sure that we keep track of where that happens at what time, and make sure that at that time, we've got a break in our velocity versus time graph. The last one, we've got a little a short duration of motion where we're moving pretty quick and then we slow down. This first part is going to be 2 meters for 1 second. So this is going to be plus 2 meters per second. For the second part, our object travels 2 meters over 4 seconds. So this is going to be plus 0.5 meters per second. That break happens here at 1 second. So I'm going to look over here at 1 second, and that's where my velocity versus time graph will change. The first second is 2 meters per second, so I'm going to draw a line up here. The second part of the motion is plus 5 meters per second, so I'm going to draw that here. So far, so good? All right. How'd you guys do on that one? That might be the trickiest one on this page. Yeah. All right. So for many graphs, both the slope and the area have physical meanings. What does the slope of a position versus time graph tell us about the motion of an object? You guys have been doing it the whole time. Ethan. Velocity. Yeah, this is going to tell us velocity. If we look at our velocity versus time graphs, the ones on the right column, determine the units for a square of the area on the graph. So if we've got velocity versus time, we're looking at a graph where we've got meters per second on the vertical axis and seconds on the horizontal axis. If we were going to try to figure out a square of that area, an area of that square, how would we do it? How do we do area? Length times height. Length times width would work too. Either way. So if we just look at the units for those, we're looking at meters per second times seconds. And so what does an area of a corner of that graph have a unit of? That was a very terribly worded question. If you make a square on your velocity versus time graph, what units does it have?
Meters per second.
What's meters per second times seconds? A meter, right? So that's what that answer should be. It should be a meter. So if I look up here and I look at one block here, if I've got 1 meter per second times 1 second, how much area does that block take? 1 meter. How about this one? Also 1 meter. What about this one?
1 meter.
1 meter. Isn't it nice? Okay, so I've got a total of 4 meters after 4 seconds. Look at my position versus time graph. After 4 seconds, I've traveled 4 meters. This is called integrating under the curve, guys. If you're in calculus, you'll see it later. All right, check out this one. If I look at this guy, how much area does this block have? That one's 1 meter. What about this one? What about like this one right here? Half. Okay, I don't like this half meter business. I'm going to get 2 of them. 1 meter. 1 meter. All right, look at this. After 1 second, I've traveled 2 meters. It's on the position versus time graph that way. After 3 seconds, how far have I traveled? I've traveled 1, 2, 3 meters.
That's crazy.
1, 2, 3, 4. So you guys have been practicing. I don't know if you guys caught on to this. You guys have been practicing going from different representations of motion. You've gone from a description to a motion map to a velocity versus time graph. From position versus time to velocity versus time. You should now know how to go from velocity versus time to position versus time. I know. So all of these are different ways of looking at the same information. And so what we're going to do is build up to the point where we can use this to solve problems. So down here where it says, what does the area under the velocity versus time graph tell you about the motion of an object? Tells you distance traveled. What would happen if you had a negative line? Like if you had a line that was a negative velocity.
It's going backwards.
Your object would be going backwards. But what would happen if you calculated this? Like what would the area of this block, if you had a line down here, what would this area be? This one be -1. Right? So I drew a straight line. It looks a lot like that straight line. If you had that as a velocity versus time graph, you would have a line that was going in the negative direction, right? So that after 1 second, your object had traveled -1 meter. After 2 seconds, it would be -2 meters. So that's the way that works. Even though it says under the velocity versus time graph, what that really means in terms of the graph is the area between the line and 0. Does that make sense? So when you draw a line that's below 0, like you don't worry about the stuff that would be under that line. You're worrying about what's happening between that line and the 0 line.
Yeah.
All right, do you guys have any questions about that worksheet? No questions? Okay. So what I want you guys to do with the rest of the time that you have today is keep working on worksheet number 3. Do you guys have any questions about worksheet number 3? Okay, I'll give you a tip. When you look at the ranking problem at the very end, the easiest way to tackle this is to go ahead and calculate your velocities for each of these and then calculate your speeds and do that before you mess with the ranking. And that should help you. All right, any other questions?
Wait, what do you rank them in?
I just jot them down on there. Like for this one, my displacement is going to be 0 and my time is 10 seconds. So this is going to be 0 meters per second. All right, our schedule's up on the board. We have about 15 minutes left. So I'm hoping that between yesterday and today that this doesn't become homework. But if you don't get done today, make sure you finish it by Monday. Just 4 long days from now. Tim and Jack online, do you guys have any questions for me?
Oh, that's my dad.